So next type of polyalphabetic techniques uh, is one-time pad, or this is also called Vernam Cipher. So why are we discussing all of these cryptography techniques? Because we want to send our message from one end to another, and secretly. We do not want this message to be read by some intruder. Right, so our ultimate goal for using cryptography is what? It is finding out perfect secrecy for sending a message. So a study by Shannon had shown that perfect secrecy can be achieved if each plaintext symbol is encrypted with a key which is randomly chosen from a key domain. So till now the techniques which we have studied, they are prone to attacks, right? So we need to use a technique which could promise perfect secrecy for sending the message. So here is one solution for that. If we use a key which is chosen randomly from the given key domain, okay, so if you are using that key which is randomly chosen, and there are more conditions to it which we will be talking, okay, so if the key is randomly chosen from the given key domain, then we can say that we can provide a perfect security for sending the message from one place to another place. So this idea, the same idea of using randomly generated keys for the plain text is used in this scheme, in this technique, one-time pad, which was invented by Vernam. So that is why we also call it Vernam Cipher. Okay, so how do we do that? How do we choose this randomly chosen key, and what should be the length of key? So these things we'll be talking about. So it says that if a truly random key is as long as the message which you are sending or which you are encrypting, then the cipher will be secure. Okay, so one point is the length of the key should be equal to the length of plain text. And second thing is that value of key should be random. Okay, so there will not be any a way, जैसे हमने previous techniques में किया है कि कोई ना कोई method से we have chosen some key and we have used that key for encryption and decryption. So यहाँ पे हम लोग क्या करेंगे, we'll be choosing that key randomly from the key domain. और key domain भी हमारे पास क्या होगा, we have these values from 0 to 25, right? So this key is unbreakable since cipher text bears no statistical relationship to the plain text, because we are using a different key for each part of the plain text. That key is never repeated for any part of the plain text. So there is no relationship, no statistical relationship between this cipher text and the plain text, right? बिकॉज जो भी हमने अभी तक टेक्निक्स यूज़ करी हैं उसमें हमने क्या किया है, सिमेट्रिक में सॉरी मोनो अल्फ़ाबेटिक में हमने क्या किया है, वी चेंज्ड द कैरेक्टर्स with all the same characters in the same way, okay, using the same key. But here in one time pad, what do we use? We use a different key every time for each and every part of the plain text. So if your plain text is having say 4 parts, say for example, if I write let's meet, okay, so here we are having these 2 parts in the plain text. One is let's, another is meet. So I will be using different key for this plain text and different key for this plain text, right? If this message have say several parts, it is having 10 parts in it, then for each and every part we'll be using a different key which will be randomly chosen, and the key which we use for each and every part will be of the same length. okay, which is this first point. So the key will be of the same length as the message, as the part of the message. So say for example, if I write it, let's meet today, okay. So for this part of the message, key length will be 4. For this part of the message, key length will be again 4, but the value of key will be different. For this part of the message, the length of the key will be 5. Okay, and it will be definitely different from these two keys which we have used for let's and meet. Right, so this thing ensures perfect security. Okay, so for any plain text and any cipher text, there exists a key mapping to one to other. So obviously plain text से हम cipher text जो हम generate करेंगे, so उसके लिए जो key mapping होगी, that will be one to other. It can only use a particular key once for the encryption. Okay, so that is the same thing I was telling you. The key will not be repeated for any part of the message. We'll be using the key only once. Okay, for any given message which is to be encrypted. Now the problem arises where when we use this kind of ciphering technique, the problem arises in generation of the key because you need large quantities of randomly generated keys, right? So generation will be a problem, the key generation will be a problem, and the safe distribution of key will be a problem. So what does it mean? It says that every message which is to be sent, a key of equal length is needed by both the sender and receiver, because the key which sender is using, the key will be used by the receiver to decrypt the message. So this safe distribution of key, passing this value of key over the insecure channel will be again a problem. So because of these two difficulties, this one-time pad is of limited utility. Okay, so where do we use it? We use it for low bandwidth channels which require very high security. Right, so we can use this kind of cipher for these kind of applications. Okay, so this is the example for Vernam cipher. Here you can see this is the plain text. Okay, so here is a single message, there are no parts in it. So these are the values, the corresponding values from the initial table. This is the key we are using. Okay, so this key will be used only once and it is randomly chosen. There is no logic behind finding out this key. Now we'll find out the value of the key letters, right? So their corresponding values will be taken from that initial table. Then while encrypting the message, this is encryption. Okay, encryption thing, and here we are doing decryption. Okay, so how do we encrypt the message? We add the value of plain text and the key. So we'll simply perform addition over here for these two values. So these values will be getting, right? Now after adding the values, we will see that if any of the value is exceeding from 26, then we'll be subtracting 26 from it, right? Because we will have numbers only from 0 to 25. So we will subtract 26 from this value, right? So we'll get 4. Rest of the values are they are less than 26, so we are keeping them as it is. So this is the cipher text which we get after finding out their corresponding entry in the initial table. So the corresponding entry for 4 is this capital E, for 16 this is Q. So this will be the cipher text which will be transferred along with this key, right? So next what we will do at the receiving end, deciphering will be done. Okay, so while decrypting the message, what will be done? the value which we have added over here, okay, this plain text and key, so that value we will be subtracting, right? So how it will be done? Yes, so the value of key is 23 over here, right? And the value of cipher text is 4. So what we will perform? We'll perform the CT, which is the cipher text minus key. So 4 minus 23. Okay, because the value of key is 23 and the value of cipher text is 4, which is for E, right? So 4 minus 23 gives you minus 19. Again, the 16 minus 12, it gives you 4, and we will just carry this process on until we reach to the end, right? So next what we will do will be, here we have subtracted these value, we have subtracted 26 from from these values which are exceeding 26. And here if we get any negative value, what we will do will be just adding the value 26 to it, right? So when we add 26 to 19 we get 7, and rest of the values are okay, they are not negative, so we will be using them as it is. So then we will check the corresponding entry in the table for the values which we have got after decryption part. So the corresponding entry for the plain text are HELLO. So here you can see that this was the initial message, the plain text, and at the receiving end this is the plain text which we have got. Right, so this is how this encryption and decryption is performed using one-time pad. Okay, next kind of ciphering technique under polyalphabetic ciphering we have is Rotor Cipher. Okay, so now in Rotor Cipher, what do we do? We use a series of cylinders. Okay, cylinders as in they have 26 pins. In cylinders we have 26 pins, 26 for input and 26 pins for output. The output of one cylinder will be acting as the input for another cylinder. Okay, and one more thing, that we can rotate these cylinders, right? So here you can see this rotor is, it is telling you that you can rotate these cylinders which we have created over here. So for when we implement this cipher, when we then we have cylinders which are having 26 pins, but here this cylinder it is shown which is having only 6 pins. Okay, just to make it just to make you understand it. So what happens, uh, it uses a series of cylinders, each giving one substitution which rotated and changed after each letter was encrypted. So जैसे ही हम एक लेटर को encrypt करेंगे plain text के, एक रोटेशन किया जाएगा इसके अंदर सिलेंडर के अंदर, and the next letter will be encrypted via that cylinder which we have got after rotation. Okay, so say for example, जैसे यहाँ पे example लिया हुआ है, this is the plain text. Okay, it has 3 characters. So ये वाला जो character है, this will be encrypted using this cylinder. Okay, this letter will be encrypted using this cylinder, and the last letter will be encrypted using this cylinder. Fine. So if we are using only one cylinder for it, no rotations are there, so that would be a case of monoalphabetic cipher. See how, now what does it mean? Say for example, this BEE will be encrypted as BAA if we use only this cylinder. Okay, so you can check it, the entry for or the value which we change while enciphering it, we change this small b with capital B. Okay, then we have to check for this small e, So small e is there and its corresponding cipher text is capital A. So capital A is written over here. Again for B it will be capital A. So another capital A is written over here. So that is a case of monoalphabetic cipher, because each and every which the same character is being replaced by the same cipher text, right? So if we use these cylinders, okay, if we rotate this cylinder, then what cipher text we get? In that case, this first alphabet will be encrypted using this cylinder, the second alphabet will be encrypted using this cylinder, and the third alphabet will be encrypted using this cylinder. Okay, so here you can see this B is having its connection with capital B, so it will be replaced with capital B. Now for second character E, we have to check, we have to rotate this cylinder, and after rotation what do we get? We get this cylinder. So here also you can check, see, I'll show you. Here this rotation is one rotation. So you can see that this connection, we are moving it upwards, right? So this connection goes over here, and just like this, all the connections, they move one step upward, okay, because we are rotating it in this direction. Okay, so all the connections will move upward, right? The connections will be shifted. Okay, for the next rotation, this connection, it should move upward, but there is no connection upward, so it will be wrapped up. Okay, so where it will go, it will be going to this entry, this F. So this connection will be going over here, right? So this is one rotation when we shift the connections between different plain text alphabets and cipher text alphabets, right? So the initial setting of rotor is a secret key between sender and the receiver. Okay, so this initial setting has to be shared with the shared by both the sender and the receiver. Now this is an example of only 6 alphabets. Actually we have, as I already told you, we have the cylinders having 26 pins from A to Z, and here we are having only one cylinder at one step, right? We can have multiple cylinders also over here. So as the number of cylinder increases, the level of security also increases. Okay, so I'll show you one more example, one more diagram which uses 3 cylinders at the same position. Okay, and I'll also show you that after one rotation, how does that cylinder look. Okay, so this is the thing I was talking about. So this is the initial setting, okay, and this is after one keystroke or one rotation. So here you can see that these are the entry for the plain text, right? And what we are doing is we are moving along this input to go to the output, right? So this is the output. We are matching the same numbers over here. 24 will be matched to 24, and in this another cylinder which is at the same level, because we are using these 3 cylinders in this rotor cipher, so we'll be inputting the output which we have got from this first cylinder into the second cylinder at the same position, right? So then we again match this 24 with the output 24 of this cylinder. Then we will be inputting this output which we have got over here will be inputting this output to the third cylinder at the same position, right? So here this is 18, so we will be moving to the entry 18, right? So after this is the last cylinder, so here we will get the encrypted message. So here the encrypted message for A is what? This is B, right? So just like this we can encrypt this letter B, right? So here you move from this 25 to 25, then its corresponding pin in the second cylinder, which is 22, then you move to 22 over here, then you input the output which you have got in this second cylinder. You will be inputting that output in the third cylinder. So here you have 13, so its corresponding output is this one, and we get this encrypted message or this encrypted text for B, right? So this is how we will do for C as well. So for C we get E. So for A, B, C we get this message. What? The encrypted message is B, I and E, right? So this will be the encrypted message. Now what we will do after encrypting this message, the these pins will be rotated. Okay, the shifting of the values will be done. So here you can see that we have shifted this cylinder by one entry. So you can see over here, we are having 24, 25, 26. So we have rotated it, and this 23 which was at the bottom, it has come to the top, right? So this is one rotation. Now when we encrypt the same message after one rotation, we will get something else. So here you can see you are getting this D, O and Y as encrypted message. Here we got B, I and E, right? Now one thing over here is this cylinder, first of all will be rotating this cylinder. Okay, after 26 rotations of this cylinder, there will be one rotation in this cylinder. Okay, so and after 26 rotations of this cylinder, there will be one rotation in this cylinder. So this is how it works. जैसे हमारे जो इलेक्ट्रिसिटी के जो भी मीटर्स होते हैं या गैस पाइपलाइन के जो मीटर्स होते हैं, वो जैसे मूव करते हैं वैसे ही ये मूव करेगा, right? So this is how we use this rotor cipher. So these are some points which I've just told you about rotor cipher. It consists of a set of independently rotating cylinders through which electrical pulses can flow. Each cylinder has 26 input pins and 26 output pins with internal wiring. Okay, the pins are connected to each other. Right, so if we associate each input and output pin with a letter of the alphabet, then a single cylinder defines a monoalphabetic substitutions. That is the first case I was telling you. अगर सिर्फ एक ही सिलेंडर हम लोग यूज करते हैं जिसमें हर एक इनपुट एक आउटपुट से कनेक्टेड है, so that would be a case of monoalphabetic substitution. Now after each input key is depressed, the cylinder rotates one position. Okay, so that the internal connections are shifted accordingly. The power of the rotor machine is in the use of multiple cylinders. I told you that जितने ज़्यादा हम cylinders use करेंगे उतना ही ज़्यादा secure हमारा message encrypt होगा. In which the output pins of one cylinder are connected to the input pins of the next, as we have already seen. And with the cylinders rotating like an odometer, ओडोमीटर जैसे ये जो मैंने आपको बताया इलेक्ट्रिसिटी मीटर और ये सब काम करता है, वैसे ही ओडोमीटर काम करता है, which is an instrument which we use for calculating the distance. So it leads to a very large number of substitution alphabets being used, right? So जैसे जैसे हम लोग number of cylinders बढ़ाते जाएंगे, complexity obviously बढ़ेगी, और जो सब्स्टिट्यूशन अल्फ़ाबेट्स हम यूज़ कर सकते हैं वो उनका नंबर भी साथ साथ बढ़ जाएगा. So this is about rotor cipher. This is a picture I got for rotor machine. You can see this is how it looks. Fine. Okay, so this is how we are moving. We are just covering a number of techniques. So I thought I should make a chart out of it, and so that you people can understand that how we are moving. So initially we discussed about cryptography, and I told you that there are two kind of techniques. One is symmetric and another is asymmetric. Then we started discussing about substitution cipher. In substitution cipher we had monoalphabetic and polyalphabetic. In monoalphabetic we covered additive or Caesar cipher, and multiplicative cipher, affine cipher, monoalphabetic substitution. In polyalphabetic, we covered autokey cipher, Playfair cipher, Vignere cipher, Hill cipher, one-time pad, and rotor machines or rotor cipher. Right, so this is how we are, moving. So now the next topic which we are to cover is transposition cipher. Now in substitution cipher, what we were doing, we were replacing one character by another character, right? But in transposition cipher, as I told you in earlier classes as well, that in transposition cipher, we will not be replacing the characters, we'll be just playing with their order, right? So say for example, if you have this text name, so what you will do in substitution cipher, what do? We replace n with some other character, a with some other character, and like this. But in transposition cipher, we'll be using these four characters only, but we will reorder them. Say for example, if I write a, e, n, and m. Okay, so I am using these four characters only which are there in name, but I have reordered them. Okay, I've changed their position. So that is this transposition cipher all about. Okay, so this transposition cipher does not substitute one symbol for another. Instead, it changes the location of the symbol. Okay, that is the same thing, reordering of symbols. So these two kind of ciphers will be covering in transposition ciphers. One is keyless and another is keyed. So keyless transposition, what does it say? That you will not be using any key for it. Okay, you'll be having the plain text and you will be repositioning the letters which are there in plain text to encrypt the message. Okay, so how do we do that? In keyless transposition, the technique which we have is called rail fence cipher or rail fence technique. So how does it work? We write the plain text as a sequence of diagonals, and then the cipher text is created reading the pattern row by row. Now what does it mean? We'll be having a plain text and we'll be writing that plain text in the form of diagonals. How do we do that? See, this is the plain text I have. Okay, meet me at the park. So I'll be writing all characters in the plain text diagonally. So how many diagonals you go, that will be the depth. Okay, so here the depth is 2 because we are going up to 2 diagonals only, right? So I'll be starting writing this plain text in this way. Okay, so first I'll write this M, then the second letter E, then again you go diagonal and write E, then you write the fourth letter which is T. So that is how you move this zigzag, or we call it diagonal, and you'll be writing the whole plain text, right? So to create the cipher text or to encrypt the message, how do we do that? We will be reading this message which we have written diagonally, we'll be reading it row by row. So this is one row, okay, and this is second row. So we will be reading it row by row. So how do you read it? We read M first of all, then E, then M, then A, then T, and up to K. Then you move to second row, you read E, then T, E, T, H, P, and then R. So this will be the cipher text, right? You write it diagonally and you read it row wise and you get the cipher text. Now to decrypt it, what will you do? You'll be dividing the cipher text into two halves, and then we will be creating the rows, because the process for decrypting the message will be in reverse order, राइट. सो यहाँ पे हम लोग क्या करेंगे, पहले दो हाफ बना देंगे, जो भी हमारा सीफर टेक्स्ट है उसके दो हाफ किए. अगर सेकेंड हाफ में कोई एक लेटर कम पड़ता है दैट इज़ ओके, बिकॉज इफ द नंबर ऑफ कैरेक्टर्स आर ओड इन द सीफर टेक्स्ट, तो सेकेंड हाफ में एक जो लेटर है वो ऑब्वियसली कम रहेगा. ओके, सो हम लोग क्या करेंगे, विल बी डिवाइडिंग द सीफर टेक्स्ट इनटू two parts, and then will be forming first row with the first half and then second row with the second half. Okay, then the receiver, which is Bob, he will read the result in zigzag. So how we will do this, see, I'll show you. Here you can see we'll be creating two parts of it. So how many letters are there? 1 2 3 4 5 6 15 letters are there. So in first part there will be 8 letters up to here, right? In second part there will be 7 letters. Now we'll be writing them in row fashion, right? So अगर हम इसकी रो बना के लिखते हैं तो कैसे लिखेंगे? This will be the first row, right? And then this will be the second row. Okay, so here you can see we'll get the same thing over here. Then we will be reading it diagonally, right? After creating two rows out of it, we'll be reading it diagonally. So we will be getting the same message which was sent by the sender. Fine. So this is how we encrypt and decrypt the message using keyless transposition cipher. One more method is there in keyless transposition, which is more complex than this rail fence. So here what we do is we write the plain text row by row. We do not write it diagonally. Okay, we write it row by row, and the number of columns the sender and receiver will agree on it initially. So we'll be writing it row by row. We'll be starting from first row, then second row, and this number of columns kitni columns leni hai, that will be decided by the sender and receiver. And then we will read the message column by column to get the encrypted message. So the same message we had, meet me at the park. So what we have done over here is we have written the message row by row. Okay, so this is meet me at the, so here this is P and this is park. Okay, so this matrix we have got. Now for getting the encrypted message or the cipher text, what do? We read it column by column. Okay, so how do we read it? M, M, T, A, E, E, H, R, and so on. So this is the cipher text we get out of it, right? So this is the encryption part. Now while decrypting it, what Bob will do, he will follow the reverse process as we generally do. He will write the message column by column. यहाँ पे हमने क्या किया था? We wrote the message row by row and then read it column by column. तो यहाँ पे receiving end पे क्या होगा, will be writing the message column by column and then will be reading it row by row. So we can check for this. Say for example यहाँ पे हम क्या करेंगे, will be writing it column by column. So the first letter, second letter, third letter and fourth letter. So these letters I am taking, right? Then we have E, then we again have E, then we have H and R, right? Then we have E, A, E, K. So you can see here we are getting the same matrix over here. So the last entries are T, T and P. Okay, so now Bob has created this matrix column by column using this Cipher text, right? And he will now read it row by row. So the message will be meet me at the park, right? So this will be the decrypted form of the message. Okay, so that was keyless transposition. In the next class, we'll be discussing keyed transposition in which we'll be making use of key. So you must have noticed that in railfence cipher also and in this scheme also we do not we have not used any key over here. We are just playing with the plain text, right? So that is why we call it keyless transposition. Next we'll be discussing keyed transposition.